And our presentation is going to take you from the broad picture that we've been looking at today down to some nuts and bolts of the technology that we've been involved with. And Ivo didn't just serve his apprenticeship, he served indentured apprenticeship in Switzerland. So he has 120 years of family history in meat processing in Switzerland. So his family knows the industry quite well. On the title that's on your program, it talks about EO technology, and I just wanted to take a brief moment to explain EO technology. Electrolyzed oxidizing water, EO water, and I'll make reference to that as we go through and explain what that actually means. So what has BioStel done? We have developed an innovative and industrial grade technology, and to us industrial grade means that we're taking it out of the laboratory where we can figure out the science of what's going on, and we can bring out a technology that's quite robust. It's durable, it's reliable, it's safe and easy to use, it's quite cost effective, and that industry has a chance of adopting it because there's too much technology that we have the knowledge, but we don't know how to get it to the next phase and actually get it implemented. So what we have done also is we've developed a process of application where it's a cold sanitization process. We've worked with Switzerland on this, and in Europe, the cost of energy is a huge factor. So energy is a big cost in sanitization, and this process doesn't need the energy inputs. So the technology itself, we have developed this in Switzerland, and this is important. We used, so next Evo. We used Swiss engineering technology, and now we've been using lately German engineering and firms. And the Germans have brought a great deal of knowledge, and one of the earlier speakers referred to the German bottling industry, and we've been working with the German bottling industry to make the technology even more robust in that it is a lot of microprocessor technology that they've used elsewhere in some of their processes. We've introduced it into our technology, and so that it is, you can log the production, you can log the mixing, you can log the actual injection of the material or the application of the material, and you can log in from outside externally. So we'll take a quick look at the technology. I'm not going to spend a lot of time at this, but basically the process is based on electrolysis, and if you look at the schematic there, you see that we have two poles, the positive pole on the left, the negative pole on the right, the anode on the left, the cathode on the right. We introduce a saline solution, quite a weak saline solution, pass it into the reactor, and the reactor, we have the anode and the cathode, and we separate them by a semi-permeable membrane, and then we apply the electrical current. And when we do that, we break the sodium chloride and the water into ionic forms. And that membrane then controls the flow of those ions. So what's important is that we produce two products. We produce one out of the left-hand side, the anode, and we call that BioStel anode water, and that has a pH of about approximately less than 2.5, and it has an ORP, an oxidation reduction potential of greater than 1,000 millivolts. On the other side of the reactor, and the major constituent that you would recognize in there is dilute hypochlorous acid. And on the other side, we actually produce a surfactant with an ORP of less than minus 700 millivolts, and we have actually dilute sodium hydroxide. Neither of these materials have many mole strengths in chemical terms, so they're quite okay to handle, they're safe to be around, but they are acidic and basic in their nature. So we're going to make reference to that as we go through the rest of the presentation. So we just wanted to show you a picture because the question is, well, does this work? And here we have a picture that's just come onto the screen of E. coli, and this is our control on the left, and then we're going to treat it with BioStel EO anode water, and we'll have another picture and showing it that the E. coli start to break down. And this is a minute later, and so the surfaces of the cell are becoming rough, and actually in many cases you see them there, the lysis has begun, so the cell is breaking apart. How does this work? It goes back to the oxidation reduction potential. It oxidizes the cell surface, it removes an electron from the cell membrane, and then the cell breaks apart. So it's a mechanical action, and the scientists tell us, because we're not the scientists, that it's a mechanical action, so this would be very difficult for anything to develop resistance to. So here's a table. I'm not going to spend very much time at it because people start asking, well, would it work on this or would it work on that? Here's a list of pathogens, if you will, on the left-hand side. Only E. coli is highlighted there. And basically, yes, it works against pathogens. As we do tests for specific applications, we always have to test it against that application. Next. So we have a technology. What are we going to do with it? Well, you have to apply it to make it worthwhile. And so we have developed, again, in consultation with the European branch of the organization and the German bottling industry, a process we call ongoing soft sanitization. So it's based on HACCP, because all the plants have got HACCP in them. They've analyzed where these critical points are. What we're looking for at each point of application is a log 1 to a log 3 reduction in the biological population. We're not looking for log 7. We're not looking for sterility. We're looking for log 1 to 3. We want to use appropriate application technology. So is it a spray? Is it a mist? Is it a rinse? Is it an immersion? What's appropriate at this point in time, or at that point in the process? And what we can establish is what we're saying is an almost aseptic microfield. So at the point where a bottle cap is going on a bottle, you missed the rim of the bottle, you missed the cap. Well, it's almost aseptic right there. The rest of the room isn't. You've misted the fingers that grasp the bottle. So it's almost aseptic right there. So you go in and control a very small place on that process, but you do it again and again. It integrates into existing systems. This doesn't, where it's being applied, it's not taking and stripping out a plant and saying, well, we've got to start again. It takes what's there, how can we apply this into the system. It does enhance product quality or increase shelf life. So a better way of saying that is probably it improves food preservation. And David Hughes talked about the price pressure on food. And the question becomes, well, how much food is getting wasted through spoilage through that whole process, starting in the farmer's field, transportation, processing plant, and right in the consumer's fridge. In terms of people get concerned about the cost of their food, are they getting what they paid for? Has it got enough life to stay with them? It also increases biosecurity, which certainly in this province and in Canada, I know that the producers are all under the gun and under scrutiny around their biosecurity. And food safety. It increases food safety, improves food safety, and ultimately this reduces liabilities for everyone. So existing commercial applications in food processing, and I'm going to ask Ivo so you see a list of 4 areas where it's being applied. That's basically in Europe at this point in time. And Ivo, maybe you could just give us an example of beverage production.